I'm assuming we're up and going. I was just enjoying the song.
Wait, now stop.
Good song.
I'll keep going, sure. I'm still getting ready. Hey, looks like we're live.
Mute that.
Hey!
Yeah.
Okay, a little different now. No headset. We'll see how this goes tonight.
Oh, yeah. That's what's different about you.
Yeah, I got a little got a blue snowball mic.
Oh, terrific.
You sound like Benny.
Ain't nobody leaving here to sing the blues.
Who has a helium balloon voice? Uh-oh. Is that me? That might be. Hey, Mark. We'll have to see how my voice is coming through. Okay, we're up and running. I'm just checking the audio mixer here. Looks like we're going out okay. I think. Okay. Let me know if everybody's hearing this okay out there in Facebook land and YouTube land. Do. Hearing this okay?
Sound good on Facebook.
Okay, perfect. All right, good. Hey, let's get started then. Okay. Well, good evening, everybody, and welcome back to our Sunday night offering of Astronomy Outreach, the Sunday Night Astronomy Show. First of all, I'd like to welcome back our regular co-host, Mr. Paul Owen from the dark skies, cloudy skies of Hampton, New Brunswick. Evening, Paul. Big hands. And right from here, from Milledgeville area, where it is cloudy as well tonight, Mr. Mike Powell from the PFO Observatory here in St. John. Good evening, Mike.
Hey, but it is clearing to the west.
It is? Okay. Awesome. Okay. Yeah, this is supposed to clear overnight tonight, I think, and clear for tomorrow and clear skies tomorrow night, so that's always good.
You know something? You never introduced yourself.
Oh, I'm sorry.
Who are you?
I'm Chris Kerwin with Astronomy by the Bay. How's that? Perfect. Okay, that's all I need. That's all people need to know. That's who I am. That's who That's who I've always been for 5 years now.
For a year and a half, right?
What's that? Yeah. Well, James Taylor. See, I'm still waiting for the concert. There was a concert that was canceled back before COVID, and they wouldn't refund my money because they said they were going to reschedule it. And there were front row seats, so I can't give them up. So if I gave them up, I would never get them back again. And I'm hoping that James Taylor is going to be alive long enough to get here. It's only September, so still hoping for September. So I'm still kind of rooting for him right now, like you root for the Montreal Canadiens, kind of the same way. So.
Yeah. So did they send you a hat?
No, I bought that one. Actually, my wife got me that one for Christmas. So.
Okay.
Last time I sat in the front row, and right on his concerts, he comes right out and sits on the end of the stage during his break, and he sits there and talks to you, like kind of thing. It's just amazing. Puts on an amazing show. Right? What's that?
Give him to sign it.
I will. I'll take it with me this time. Sign it. Yeah.
You see, you have a better chance of seeing James Taylor.
What's that?
You have a better chance of seeing James Taylor than with that hat than I do of winning the cup with this hat.
Yeah, you're probably right. But hey, a man can only hope, right?
That's right.
That's right. That's what we shoot for. Dreams are made to be to happen. Okay. Well, anyway, we got another busy show for you tonight. Tonight we're going to be focused on just one topic, our sun. It's not a topic we discuss very often, but with the excitement around the recent partial solar eclipse, we thought it might be a good time to devote a program to it.
I thought we were doing the moon.
Well, they're both about the same size in the sky. Maybe some people might not know the difference. Anyway, so tonight Mike's going to offer a talk on the mechanics of our sun, what's the solar cycle, what are sunspots, what are solar flares, and why they are important for us to watch, keep an eye on. Also tonight we're going to take a look at some of the past and current space missions that helped us determine most of what we know about our star. And just because we are past the eclipse doesn't mean that the sun is not interesting to observe, so Paul will hopefully show us how we can continue to safely look at the sun, as we did through the eclipse, but we can still look at it now with sunspots and solar flares. So, also tonight, Mike's going to be offering another Binal Bud target of the week, and Paul will be back with another interesting Rosanna's Fun Fact segment. And we're going to have all of your wonderful photo submissions. I did ask for a few pictures, please, of sunrises and sunsets that I might be able to share tonight. Well, I get 85 photos in. I was like, whoa! Yeah. Be careful what you wish for, because this might come true. Anyway, so I got those in a little bit of a clip here. We're going to show them a little bit later. So sit back, folks, and enjoy. And remember, this is a family-friendly live broadcast. So if you happen to have any questions about the night sky, we're more than happy to try to answer them here for you. So let's get started then with the talk from Mike about our sun. Mike's going to start us off.
Alrighty, wow.
Oh, and Paul's going to mention something about a course that he's offering too. We're going to get to that tonight.
Yeah, we'll get to that a little later.
Okay.
Shuffle some screens around here. Ew.
So we'll be waiting for JT here in London too. Sari's going to appear here first in September, I hope. No, that'd be great. Looking for JT as well. Awesome. Okay.
If you can see that, we're probably ready to go.
I'll be quiet.
Yes.
Just let me try to pin that, Mike. Hang on a sec. I think I can pin it just a little bit larger. Change layout to a spotlight. And there we go. Okay. All set.
The sun is our topic of the evening. It's easy to spell. It's hard to make a spelling mistake when I was putting this one together. What is the sun? The sun is the most prominent feature in our solar system. It's the largest object and contains approximately 98% of the total solar mass. That is huge. 109 Earths would be required to fit across the sun's disk, or you could put 1.3 million Earths inside it, just to give you some perspective on its size. The sun's outer visible layer is called the photosphere, and has a temperature of 6,000 degrees Celsius or 11,000 degrees Fahrenheit. This layer is a molten appearance due to its turbulent eruptions of energy at the surface. Kind of looks like water boiling, actually, and I'll get to a slide that shows that. So what's the sun's makeup? Well, if you go down this list and look at the numbers on the picture, number 1 is the core, number 2 is the radiative zone, number 3 is the convective zone, number 4 is the photosphere, 5 is the chromosphere, 6 is the corona, 7 will be sunspots that show up, 8 is granulations, and 9 are the prominence or flares. And those are the things that make up our sun. The core, the sun's energy is created deep within the core of the sun. It is here that temperatures of 15 million degrees Celsius or 27 million degrees Fahrenheit and pressure of 340 billion times Earth air atmospheric pressure at sea level is so intense that nuclear reactions take place in the center. This reaction causes 4 photons of hydrogen nuclei to fuse together to form one alpha particle or helium nucleus. Boy, you think I've been drinking? All right.
Sunstroke.
Yeah, exactly. I just not in this weather. The sun has several layers. Okay, the core, the radiation zone, the convection zone, and the photosphere, which is actually the surface of the sun that we see. In the nuclear reactions that occur at the core, about 700 million tons of hydrogen is converted to helium every second. Those numbers are hard to fathom.
Wow.
Helium is about 7% lighter. This means that 5 million tons of matter per second is converted into pure energy. This energy, believe it or not, takes about 10 million years to travel from the core of the sun's photosphere, a 500-kilometer thick layer in which the sun's radiation and light finally escape. So 10 million years to go from the surface out to the edge, just so we can see it. It's unbelievable, the numbers. The chromosphere is above the photosphere. The solar energy passes through this region on its way out from the center of the sun. Facula and flares arise in the chromosphere. Facula are bright, luminous hydrogen clouds which form above the regions where the sunspots are about to form. And flares are bright filaments of hot gas emerging from the sunspot regions. And you can see as that rotates around the different facula and flares. Excuse me. Now we'll get to quickly about sunspots. At sunspot minimum or solar minimum, the magnetic field is relatively straight, like lines of latitude. Because the equator rotates faster than the poles, which is called a differential rotation, as time goes on, the fields get twisted up, almost like rubber bands getting twisted. During the course of 11 years, the magnetic fields become so twisted and tangled that the field breaks through the sun's surface, causing sunspots. And you can see on the top there, in that top photograph as it spins, how those get all twisted out of shape. And as soon as they get all twisted up, excuse me, that's where the sunspots form from.
Can I get you to hold just for a sec, Mike? I'm seeing somebody saying that there's a bit of an echo. I'm just going to try a little something here. I'm just going to try to mute my mic and see if that helps.
You know, one of my coughing fits here. Sound better?
Well, my mic is muted, so I'm not sure. But you go ahead. I'm going to turn off the mic. It should be okay.
So that's how the sunspots get formed. And we can only see them because the sunspots are actually cooler than the rest of the sun. So when we're looking at dark sunspots with a white solar filter, we're actually looking at areas on the surface that are cooler, kind of like you're looking in. The process of tangling is stopped when the system suddenly relaxes to straight lines and the sun's overall magnetic field reverses for the next 11 years. So that's where sunspots come from. And you can see here, solar minimum and solar maximum. There's quite a difference with those magnetic fields getting all twisted out of place. Sunspot consists of a couple of different parts. You got the umbra, which is down in. It's like you're looking into a hole down in. And the umbra is the dark spot down in the middle. The penumbra is kind of like the waterfall sides pouring into it. And then on the outside edge of the sunspot, you got the granulations. Now, the granulations are pretty cool. The regions of the sun where hot solar material comes to the solar surface. The granules are about 600 miles or 1,000 kilometers across and only exist for about 5 to 10 minutes before they fade away. It's almost as though the surface of the sun is like a bubbling pot of boiling water. So you can see the granules there, and it looks exactly like boiling water. And you can pick those up in a photograph, or you can pick them up if you got good focus with a white light solar filter. A solar prominence, also known as a filament, is an arc of gas that erupts from the surface of the sun. Prominences can loop hundreds and thousands of miles into space. Prominences are held above the sun's surface by strong magnetic fields that can last for many months, or just a day, or even shorter. At some time in their existence, most prominences will erupt, spewing enormous amounts of solar material into space, and that's what we call a coronal mass ejection. So a coronal mass ejection, or CME, are violent discharges of material from the sun's outer atmosphere. This ejected material can travel at speeds of up to 1,000,000 miles per hour. If this flow of charged particles and embedded magnetic fields collides with the Earth, it can dramatically disrupt the Earth's geomagnetic field and ionosphere. And it can disrupt satellites. It can disrupt our power grid. It can cause some major grief. If a CME was pointed directly at the Earth and hit us. I think back in 1984 or 1989, was it? They had the big power outage in the eastern coast of the States, and that was caused by a CME. The auroras. When a coronal mass ejection reaches the Earth, excuse me for a second. I got this tickle in the back of my throat that won't go away. So when a CME reaches the Earth, it may disrupt the Earth's magnetosphere, compressing it on the day side and extending it on the night side. This process can cause particularly strong aurora in large regions of the Earth's magnetic poles. These are known as the northern lights, or the aurora borealis in the northern hemisphere, and in the southern lights, aurora australis in the southern hemisphere. Coronal mass ejections along with solar flares of other origin can disrupt radio transmission, cause power outages, and cause damage to satellites and electrical transmission line facilities. Like I said, if the CME is strong enough, it could really wreak some havoc. So the northern lights, the bright dancing lights of aurora, are actually collisions between electronically charged particles from the sun that enter the Earth's atmosphere. The lights are seen above the magnetic poles of the northern and southern hemispheres. They're also known as aurora borealis or aurora australis. Australis? I don't know. I can't pronounce that. Auroral displays appear in many colors, although pale green and pink are most common. Shades of red, yellow, and green, blue, and violet are also been reported. The lights appear in many forms, from patches or scattered clouds of light or streamers, arcs, and rippling curtains, and shooting rays up into the night with an eerie glow. And you can see the picture there, just a quick video of just ribbons of how the northern lights go. And I guess it's incredible when you do see it. I was fortunate enough to be up in the Northwest Territories, and the whole sky it turns to daylight with blues, reds, and greens. It's amazing. They say you can almost hear it. It is an incredible sight if you get a chance. I guess Iceland is well known for the northern lights. Anyway, that is a quick shot about our sun. It explains the sunspots and aurora borealis and coronal mass ejections and all the good stuff that the sun has to offer us when it takes its time. Anyway, that's the end.
Wow. It's so amazing, we get up and we look out, see the sunrise, and all we see is just a point of light in the sky, and all we think that it energizes us and lets us see, but we wouldn't even consider all of those things that you had talked about. But if you want to study the stars, you just study the stars, but you got one, the biggest one, not the biggest one, the closest one, right out, and you see it virtually every day. I mean, what a thing to study. I mean, you could spend years studying that thing.
True. Yep, very much. I mean, the sun, if it wasn't for the sun, we wouldn't have life here. It controls everything about us, right? I mean, the sun provides us energy, light, heat. I mean, it's given the fact of life being able to form here. It's been doing what it's been doing for 4.5 billion years now. We still got another 4.5 billion to go. But I mean, it's not the largest star out there. It's certainly the largest in our neighborhood, but it's about larger than about 80% of the stars out there. And it's crucial for us, and especially now with so much electronics, satellites, and things up there, we really have to pay attention to what's happening with the sun. There's something called space weather now, where meteorologists, I'll say, study the sun, and they'll watch the activity happening on the sun. And if there happens to be a CME or coronal mass ejection, large billions of tons of plasma heading in our direction, they'll warn companies to tell them that they might have to harden their satellites or turn them down while this storm passes through, right? So it's a very, very crucial part of our economy at the moment, our society at the moment, to be aware of what's happening with our sun, and hopefully not of our economy.
Did I read that whole last part muted? Because it looked like my microphone was muted there for a bit.
Nope, you heard everything.
Good.
Okay.
Yeah, there was some
I
echo.
got it, I seen the mute, and I went, "Oh, did I miss turning it back on?"
Well, I think you can barely hear you, Chris. Now, okay, so that's me. So I'm playing around a little bit with this external mic. So I'm going to turn my mic back up again, and we'll see if we get any feedback from the guys again. When you guys do presentations, I'll just mute my mic. So
Yeah.
okay, hopefully that's better. It does free me up a little bit without the headset for sure. Okay. Let's go from there to, I can do my little bit of presentation, I guess, on space missions. Okay, let's go out with that one. Okay, and just need a second here. Open this up.
Someone was saying they could barely hear you, Chris.
Yeah, they were saying that. They just commented there that it's better now, I guess. So
There we are. Yeah.
I did have my volume turned down on the broadcast software, just so
I don't read that fast.
I wasn't getting any feedback. Okay, let me first of all, before I start this, I gotta. You guys, they're seeing it out in Facebook land, but you guys aren't seeing it. So let me present now. And I want to go with the screen. And you guys should be able to see that now.
Yep.
I'll do this. Oh, now you should be able to see it.
I do.
Okay, let's go from the beginning.
Yes, indeed, duty.
Okay, so it's displaying on the wrong screen, of course. Just a second. It's doing that on me. I don't want to tell these people about the issues I had with the computer before. But all of a sudden now it doesn't want to display it properly. So what I'm going to do here.
Well, you know, in the beginning, the issues with the computer were part of the show.
Oh, they were?
Yeah.
Yeah. We can say that. Let me see if I can get this to come up on the right screen. No, it wants to keep coming up on the other screen on me. So I guess what I'll have to do is just present it with the main screen showing up. This is what happens when you're live, folks. Okay, we can talk about it this way, I guess. Anyway, our sun and the many missions that we've used to study it. So since 1960, we've been actually looking at the sun. There's been a lot of missions towards the sun. That we've had over 20 missions so far that have taken their time to go out and take a look at the sun. They've all been orbiters, of course, but they've all provided different types of information. From 1960-69, there were 6 missions from NASA. From 1974 to 1977, there were 7 more missions. From ESA and NASA, combination of missions. SOHO, there's a few others here we're going to talk about for just a bit. And from 2000 to present, we've had 8 missions, and there's actually one that's on its that's going to be launched next year, another mission to study the sun. But probably the one that's doing the most work right now is the Parker Solar Probe, which we'll look at that in a second. Everybody can see this okay? Sorry about the way I'm presenting here.
Looks good on Facebook.
Okay. So stereo A and B, and I don't think it's going to let me take that link. Let's try this. Control click. Oh, it does. Look at that. Okay, so we can get there. Let's go back to my presentation again. This is what happens when screens get all mixed up. 1 second. Please bear with me. We're live. We're live. Okay, so stereo A and B. I'm just going to talk about 4 different missions that are out there. There's lots of them, like I said, but the 4 that I'm going to talk about are these ones. Stereo A and B from 2006 to present. It's actually only supposed to have lasted 2 years, and it's been going now since 2006. So not bad. 15 years of getting out of these robotic spacecraft now. So there's 2 nearly identical spacecrafts that were launched back in 2006 into orbits around the sun that caused them to respectively pull ahead and fall gradually behind the Earth. Now this enables the stereoscopic imaging of the sun and solar phenomena such as the coronal mass ejections that we talked about. Contact with Stereo B, though, unfortunately was lost in 2014, but Stereo A is still operational. Now the principal benefit of the mission was really to give us stereoscopic images of the sun. In other words, because the satellites are at different points along the Earth's orbit, but different distances from the Earth, they could photograph both sides of the sun, especially parts that are not visible from Earth. So we could see sunspots on the other side getting ready to come around to our side of the sun. So that's not possible now. We can only see them as they come around the crest of the sun, which is unfortunate, but that's what happens, I guess, sometimes with spacecraft. So let's go try taking a look here. So here's the website, and again, it was supposed to provide a 3D view of the sun and Heliospheric, and this is our view that we can get from the Stereo A right now. Anyway, again, there's no data from Stereo B at all, but one of the sites where we can get stuff. Okay, I'll go back to the presentation. This next one up would be the SOHO, which is called the Solar and Heliospheric Observatory. It was launched in 1995, and it's still going. Planned 2-year duration, still functioning 25 years later. Pretty good. These guys are getting really good with these spacecraft. Like, I know they're spending $1 billion on them, but really they're getting very, very good with these robotic spacecraft. Lifespans are just 10 times what they expected, so they're getting 10 times the science out of it as well. The 3 main scientific objectives of SOHO are investigation of the outer layer of the sun, which consists of the chromosphere, as Mike said, the transition region, and the corona. Making observations of solar wind and associated phenomena in the vicinity of L1, which is the Grange point, which is basically it's a balance point between Earth and the sun, and probing the interior structure of the sun. Again, if we click on this one, it should take us to the link. This is the Solar and Heliospheric Observatory. These are the sun now. These are actually showing us images of the sun in different wavelengths of light. This one actually has the sun blocked out right here. So that's showing the disk of the sun blocked out, but we're showing solar streams that are leaving the sun from huge solar flares that are happening right now on the sun. These are large streams of plasma, billions of tons that are exiting the sun right now in the solar wind. We've got various other views, like this is the one that we would get in H-alpha. So if we had a special hydrogen alpha telescope, this is what we would see through it. The sun would be this color, I'll call it, but it's a very thin, narrow band of the spectrum of light that allows us to see solar flares, and these would be groupings of sunspots here, but it allows us to see solar flares and ejecta leaving the sun, large loops of plasma, and also the granulation on the surface of the sun as well. I mean, here's our normal sun, sun through a normal telescope that we could see sunspots. So here's a grouping of sunspots here that is, I believe it's about 4 times the size of the Earth at the moment. So these are very large. It would take 110 Earths lined up in a row to completely cover the disk of the sun this way, horizontally. So 110 by 110 by 110 deep, that gives you about 1.3 million Earths would sit inside the sun. From there, back to the presentation again. And this one. From there, we've got the Solar Dynamics Observatory. Its planned lifespan was 5 years. It's now been going for more than 11 years. And the goal of the SDO is to understand the influence of the sun on the Earth and near-Earth space by studying the solar atmosphere on small scales of space and time in many wavelengths simultaneously. From this one, we can probably take us into that link. And there's our sun right now. So we're getting constant images of the sun. There's our sun in well, I guess it would be H-alpha, very close to it. Another view, there's our H-alpha view. That's one we would see through small solar scopes. In X-rays, ultraviolet, all different wavelengths of light. So we can see different calcium K, different types of light that allows us to see different features on the surface of the sun and throughout its chromosphere as well. That looks pretty mad, doesn't it? So this is all live. This is all live, like the very recent views within the last few minutes or so. So if you wanted to find out what's happening with the sun, you can go to this website and find out, or you can go to a website called spaceweather.com, which posts up regular information about the sun as well. The last one I want to talk about really was the Parker Solar Probe, which is the big deal right now. The Parker Solar Probe was launched back in 2018. Its planned mission is 7 years. It's elapsed, I guess, almost 3 years now. And its primary mission is to make observations of the outer corona of the sun. They say this spacecraft will touch the sun. That's the big, term apparently, but it's not going to touch the sun. It's going to get very close to the chromosphere of the sun. It will approach to within 6.9 million kilometers from the sun, though, and by 2025, will travel at its closest approach as fast as 690,000 kilometers per hour, or 0.064% the speed of light. So it's looping in around the sun and coming back out again, looping back in and coming back out, and these orbits that it's making are causing it to speed up. and it doesn't want to spend very much time in that area. That's the thing. As it gets closer to the sun, it's going to spend less time in there because it doesn't want to fry itself. It does have a large heat shield in the front, and it actually has a radiator on it that sends cooling liquid out around the electronics, to cool the electronics, and as it gets out to the back end of the spacecraft, it cools down because that's facing the blackness of space, right? The Parker Solar Probe is the first spacecraft to fly into the low solar corona. It will assess the structure and dynamics of the sun's coronal plasma and magnetic field, the energy flow that heats the solar corona and impels the solar wind, and the mechanisms that accelerate energetic particles. So lots to do with that one, lots to see with that one. That's the one we want to follow closely. That's what's going to give us a lot more information about the sun. Now we'll see if this plays or not. And you'll have to let me know out there, folks, if the audio works. So let's try this.
Traveling through the sun's blazing hot atmosphere, NASA's Parker Solar Probe has sent back a complex, close-up view of our star. The spacecraft confirmed that our picture of the sun from Earth is deceptively simple. Parker is the closest spacecraft to the sun, meaning we now have never-before-seen details about the solar wind and solar energetic particles.
I'm going to pause that just for a second. I'm going to try to turn off my mic so it doesn't backfeed. Just 1 second.
Solar energetic particles are high-energy particles that can endanger both astronauts and satellites in space. The solar wind is the continuous outflow of particles and magnetic field from the sun. Both speed out, filling up space and affecting space weather throughout our solar system. For the first time ever, we were able to go to the source of the solar wind and solar particles. Here are 5 features Parker saw. We've long known that space is full of cosmic dust. We can even see the dust from Earth because it reflects sunlight. Parker saw evidence that the dust stops at an estimated 3.5 million miles from the sun. As the dust gets closer, the sun vaporizes it, creating a dust-free zone surrounding the star. At Earth, it appears that the magnetic field lines flow evenly out from the sun, but Parker saw them behave in a surprising way. The magnetic field lines flip in a whip-like motion, turning 180 degrees around in a matter of seconds. These switchbacks came in clusters and were timed with fast-moving clumps of plasma in the solar wind. Scientists have long wondered if the solar wind is generated as a continuous flow or in spurts. We now see evidence that the solar wind has rough, irregular texture. The plasma within it also seems to lack an orderly sense of direction. Some clumps of solar material fire out into space, while others fall back toward the sun. These clumps may be distorting the magnetic field, causing the switchbacks. They may also be an indicator of what the solar wind looks like in its early stages after its birth on the sun. Parker found a transition point in the solar wind. The corona is the sun's faint, outermost layer that transitions to the solar wind. Before Parker, scientists knew that the corona rotates with the visible surface below it, but they didn't know how, or where, the solar wind switched to flowing straight by the time it reaches Earth. Parker has finally spotted signs of this transition, and the changeover happened significantly farther out than expected. Although the sun has been very quiet over the first 2 orbits, Parker observed several tiny bursts of solar energetic particles. While these events have been seen before, never ones this small. The fast-moving particles from these modest bursts spread out as they move from the sun, making them undetectable from Earth. Without Parker's front row seat, we would never know that the sun is regularly producing these small-scale events. Fast-moving particles are a source of dangerous radiation. The more we learn about these eruptions, the better we can protect our technology and astronauts. Parker still has more work to do, but it's already helping us see our star in a whole new light.
Okay, so that's about it. This is the guy we really want to watch for those, is the Parker Solar Probe. It's going to be the one that's going to bring us the best research in the next few years for sure. And,
It's pretty amazing that we can send a craft. Oh, what do you got?
Okay, that's it.
Oh, that's so funny.
Get rid of this, get rid of this, get rid of this, get rid of this. This, I hope I won't close the channel out. Hey, we're back. Stop presenting. There, I'm back now. Hey,
Right.
okay.
So anyway, I was saying that it's just amazing how they can take a spacecraft, build it here, get it that close to the extreme temperatures that both of you guys are talking about, and be able to take data from that. The whole thing just blows my mind.
It's like the thing about that spacecraft too is it travels at 600,000 kilometers per hour.
Yeah.
It's autonomous, right? So it has to make its own decisions. So if it just happens to turn a little bit towards the sun, too much, it's going to fry the electronics. So it has these probes that stick out either side. There's two up here and two on the bottom, and they're measuring sunlight. And if they happen to see a little bit of sunlight, it'll turn the spacecraft back again. So it has this huge heat shield in front, and all the electronics are kind of buried in behind it. And it has this radiator that helps the cooling part. But yeah, just to know that it can operate on its own, and that's what they're designing a lot more into these spacecraft is the autonomous feature, because it's 8.5 minutes to get to the sun. So it would take us 8.5 minutes to send a message to it and for it to receive it back. But when you're talking about Mars and Jupiter and Saturn, you're talking about hours for messages to get there and back again. So you have to make these craft more and more autonomous. And let them make their own. So it's all AI, right? Let them make their own decisions, and that's where.
But just in the intelligence that they put into these crafts.
Yeah.
I mean, think about that. I mean, a computer's thinking the way we would think.
Yep.
You know, it's just actually better than we would think.
Better, yeah, and faster, and I mean, but it's the amazing people that work at NASA, JPL, and Goddard's spaceport. It's the people that they bring in, the engineers. They're so challenged, but the stuff that we've been accomplishing over the last 20 years or so, it's just been phenomenal. The amount of information we know about our solar system now, and to study the sun, which is really the primary object in our solar system, we need, and again, it's a safety issue that we have to be concerned about, because all the sun has to do is burp, and we have to go, whoa, hang on, So we're really under its control, under its whims, basically. So
yeah. And if it gets too hot for that craft, they can just wait until nighttime and cool down.
Yeah, on a flat Earth. You could.
I just close the curtains.
Oh boy.
Blinds up.
Okay, we'll leave that topic alone. So we're going to go next. We got a Vinyl Bud talk. We got a Rosanna talk.
And pictures.
And pictures. I do have some pictures. But it's about 4 minutes long, so it's not bad. So we can show all those pictures that we had brought up. But one of you guys want to talk first, or you want to get them over first, or?
Well, don't scan them through them too quick, because we want to be able to see them.
That's true. Yeah. Well, I can go ahead with that now if you want. Doesn't matter. Or Vinyl Bud.
Yeah. We took it last time, and we're only at 22.
Okay. Well, did you want to mention your course, Paul, first, or?
Oh, right.
Let's go with that.
Of course.
Okay.
Of course.
Yes.
In actual fact, it's actually not a course. It's a hangout, and I just want to explain what that is, what we're doing. So starting on tomorrow night, actually, and I'm going to do this every Monday night until there's just no interest anymore. And what we're going to be doing is we're going to be doing sort of a hangout for those who want to learn and talk about astroimaging. And that don't mean that it has to be technical and thousands of dollars of equipment. It can be just a camera on a tripod taking Milky Way. So we'll be talking about everything, something as simple as that to something as complex as using LRGB filters and how to process all that data and make a picture. We're going to talk about software, what software to get, and the softwares that at least that I'm familiar with. I'm going to do demonstrations on all of it. So we'll be talking about PixInsight. We'll be talking about Photoshop. We'll be talking about AutoStacker, RegiStacks, all of those different software, PhD guiding, all of those things that you have to acquire and understand to use in order to be able to get the images like the one you see behind me. That kind of stuff. But at the same time, we're also going to be talking about equipment. So we're going to talk about cameras. We're going to talk about mounts. We're going to talk about telescopes. And I don't mean just one for observing. And of course, you can observe. But, when you're considering something for imaging, what are the considerations and how do you match a camera to a telescope, and and all those sort of things that you have to consider. So that's kind of what this sort of hangout is going to be. Now I'm going to be hosting it through Google Meets, just like this, and so far I've got 10 people that are going to be participating so far, and all we want is for those people who are thinking about getting into imaging or are into it and they want to kind of bring it to another level. Come on in, and it's not a commitment thing like in a course where you're committed to so many nights. This is a hangout. So basically it's like, give us your ideas. Whatever your ideas are, we're going to talk about them. Now, it may not be that week that we're going to talk about it because we're going to be talking about so many things. So that means that if you send in an idea and I say, you know what, I'm going to do a talk on that, or we're going to talk about it, or I'm going to do a presentation on it, I'm going to set it up, say, for 2 weeks from now. So that means if you're not interested in the other stuff, well, then stop in 2 weeks from now. Now, what I've done is I've set up a Facebook page. It's a private Facebook page only for the people that want to participate in this hangout. And it's private, which means you can't search it from public. You have to get it from me. And if you want to get into it, I have to let you in. And the reason I set it up is because between weeks and sessions, I want that page to give life to all the people who want to connect with each other and maybe share ideas and talk about things. And, what did you do? And what are your experiences? And I tried that this week. And how did you make out? Just to keep the chatter going all week long, and a place that you can go and get support. And at the same time, it's a place that I can put the link so that each week, instead of me passing out links to each individual person, you just know to come on to that particular Facebook page at 6:30. The link will be there, and you can click on the link, and then you can get in for that week's session. So that way there, you don't have to worry about, oh, geez, he forgot to put it up, or he missed a person or didn't miss a person. It'll be up to you just to go onto that page, which you're going on to anyway, and get the link for the evening's offering. So that's basically what I'm setting up to do. So as the season wears on and we start to get into darker evenings at the 7 or 8 o'clock hour, then I'll actually have my observatory running, and I'll be doing an imaging session. And as I'm doing that imaging session, then we can actually go ahead and talk about all the things that you need to do to prepare, all the things that you do when you're troubleshooting. Oh my gosh, this happened. How do I fix it? So we'll cover all kinds of cool stuff. And at the same time, again, DSLR on a tripod with a shutter remote, taking Milky Way pictures, how to process it, how to stack up your images, how to get some bias or some calibration frames, all of that stuff. So we're going to cover everything. So that's what's going on. So if you want to send me a Facebook message, I can send you the information to what that Facebook page is. And but tomorrow night is the very first session, and it's going to be at 7. So I'll be sending the links out about 6:30. Awesome.
Okay, sounds great. Yeah.
That's it.
So they message you through Facebook to say they want to join the page. Is that how they do it?
That's exactly it.
Okay.
And then I'll let you into the page.
Yeah.
And then the first week I'll probably send links out to everybody just to get everybody familiar.
Yeah.
But if you're already on that page, then basically each week the link will be there. So you just have to go there and get your link. And if you're going to join that week, just go to my page or that page and just click on.
And all free of charge.
All free of charge, no charge.
No charge. Awesome. That's what we like. Here we go. So we got a lot of people already saying here, count me in, I'm in. Yep, great. So yeah, beginners are welcome for sure. Beginners, intermediates, and advanced. Doesn't matter what level you're at. Paul is your man for helping you out with your photos. Absolutely. And it's all free, so can't get much better deal than that. What's free today anyway? Nothing.
No.
Not much.
No, but it's just that we're, just like what we do here. It's just that we're passionate about what we do, and it's just nice to give back. I had a lot of people help me over the years.
Yeah, and it gives you value to get out your information as well.
Really turn around and help other people. So
yeah, awesome. Thanks, Paul. Great.
Right.
So everybody keep that in mind. I'll put it up on my Facebook page now that Paul's released the information too, and I'll put up some information about what he wants to do. So I'll get Paul to do a little write up, and I'll share it on my page, and then he'll explain everything on that. So
well, actually, if you go to the St. John Astronomy Club site,
okay,
it's there.
On the website or the Facebook page?
Little explanation of what we're doing. But I will prefer, I'll give the page name.
Okay.
To to the people.
Okay, sounds good. All right, we'll get that up there.
Yeah, thanks.
Is it good for bridge cameras? Not sure what that means.
I don't have a lot of experience with bridge cameras, but you know, it won't be much to figure it out.
Okay.
Yep.
All right, awesome. Okay.
Yep.
So let's look forward to a good turnout there. Should be great.
Yeah.
Good way to. And how do you get the clear skies, by the way? Anyway, on Monday nights. So how are you getting clear skies? Because we can't get to seem to get them on Sunday nights. So
That's the beauty of having data over the few years I've been doing this. It's if it's a dark night, we still have data to play with.
So you're going to pretend that you're imaging something then?
I'm just pretending. Well, I mean, some of the targets I've been putting up lately aren't even in the sky in our view. We've had enough of a cloud.
Yeah. Let's show you Orion. Here's how I image Orion. Wait, now, Paul, Orion's up in the wintertime. What's going on?
Yeah.
Okay, let's go from there to, we've got Bino Bud and we've got a Rosanna talk and we've got some photos to show. So you guys can choose. What do you like? What's your pleasure? I'm good for anything. Don't matter to me.
You want a bud?
Bino, let's do a Bino Bud. Okay.
Give me a bud.
Give us Bino Bud.
Good.
Okay, let me,
He likes our good.
looks good. Just a second.
Yeah, we should.
1 second, I'm going to pin that now. Change the layout.
Should have a bud.
This bud's for you.
Yes.
Go ahead.
I hear an echo. Echo. All right. Binocular target of the week by Bud O'Bud is this week Messier 27 or the dumbbell. Although M27, the Dumbbell Nebula, is not the only planetary nebula that is visible in 10 by 50 binoculars, it is sufficiently easier to see than others. But you need a large instrument with more magnification to show some of the internal structure. How do you find it? Well, for me, if you find Sagitta, which basically looks like a little sideways Y in the sky, you come up to the top star and go straight up to M27. At midnight is when you're going to find this at about 120 degrees east, southeast. So again, it's still relatively early, but if you go out and we all look around and find Deneb, Altair, and Vega for the summer triangle stars, you come up from Altair straight up and you'll find Sagitta, and then from there you can find that top star and go straight up and find M27. While you're sweeping up through there, you might come across what's called the coat hanger as well. But if you can look up and again find that summer triangle, if you took a straight line between Deneb and Altair and you come up about 1/3 of the distance and just off to the right a little bit, that's where you'll find M27. And it's actually a pretty easy target to find. It's not that difficult. What will you see? Well, this is M27. It's a planetary nebula. It looks beautiful, but you won't see it in color, and you won't see it quite so big in binoculars. But what you will see is this in 10 by 50s. So you get the star field around it, and you will find that little cotton ball almost dead, if you find it dead center. And that's what it'll kind of look like, a little cotton ball in the sky. Now, for comparison, again, I brought up the full moon, and M27 is, probably a little bit smaller than the Sea of Tranquility. So it should be relatively easy to spot, actually, against the background sky. It's not as small as it kind of looks in this photograph. It's a little bit bigger. And we have our... Now you know why they're clearing the forests in BC.
Hey, Stefan's got that very thing in mind.
Exactly. That's our Bino target of the week from Bino Bud.
That's fantastic.
Awesome. Thanks, Mike. Okay, there are a couple of questions here. Enjoy the Decline on YouTube is saying, is it true that a massive solar flare is imminent and causes another Carrington event? Imminent? Well, probably imminent in the 4.5 billion years of the sun's life cycle to come. But how soon? I know they were saying about every 100 years or so. The Carrington event, of course, was the huge solar flare or coronal mass ejection from the sun that affected the telegraph system actually in North America and around the world, I think. Burn up telegraph parts, pieces, and it actually. Oh wait, now I'm thinking. Yeah, Carrington event. Yeah, it was a Carrington event. Yeah. So yeah, is it going to happen again? Most likely, yes. Astronomers do predict that there is one about every 100 years like that. But now, if we had one around now, just think about the damage that it could cause with our satellite system or our Starlink satellites, or it would affect us globally. The incident that Mike was talking about earlier, the one in Quebec, was in 1989, and what happened was there was a huge solar flare at that time. It released tens of billions of tons of plasma towards our planet. Our magnetic field protects most of us, but what it did was it actually penetrated through the magnetic field, and it induced a current in the power lines in Quebec. And of course, with power is the only thing that's actually consumed the instant that it's produced, right? So when it does happen like that, you've got safety switching throughout. So when it induced this current into the high voltage lines in Quebec, it overloaded some of the circuits. They tripped, and then other ones would get that extra power. They trip, and it would just continue to just massively spread throughout the whole province of Quebec. And for, I think it was 12 hours at least, the province was completely black, just by a solar flare. So
the other thing you got to look at is when the CME happens, and they're happening all the time, and there are some massive ones. In order for it to cause a problem with us, it has to be pointed towards us.
Right.
Right. We're just a little dot in space way out here away from the sun. If that's just off a little bit, it can miss us.
Yeah.
We can catch parts of it, which will cause the auroras to get bigger and so on and so forth. But unless one of those large ones is pointed directly at us, it's like taking a yardstick and trying to swat an orange in space, right?
Yeah.
It's got to be pretty much bang on before it causes us too much damage.
And even if we're in direct line with it, it takes 3 days to get here. So we're going to be in a different location in 3 days' time. So it may miss us that way. So it has to be lined up almost ahead of us, and burp, and then us, move into it, kind of thing. So, but yeah, some of these storms can be huge. It spits out plasma at the rate of 1 million miles per hour. The solar wind leaves the sun at 1 million miles per hour. Well, it's still 93 million miles away. So you're talking almost 4 days, to get here, right? So. But we can see that happen, and we can tell that that's why we have all these spacecraft out there right now to watch the sun continuously, to see if anything is going to happen. And they would warn companies with satellites, to tell them to harden up and to get ready for this activity coming. Even power plants, everything else would be. If it was that big, it would be a global announcement basically to let people know, because it could affect our economy for a long time. Once you start taking out huge transformers in large power grids, there isn't a big stock of these things sitting in a warehouse in Amazon somewhere waiting for you to buy them. They're just made basically, as they're required. And with everything that we're going through lately, trying to even get stock of anything, you can imagine if you dropped a power grid down, in a big province like Quebec, how long would it take to get that material back again, right? So it could be a long time. So. Okay, after all that, so that was that answer, I guess, to that question. I think, maybe not, I don't know. We're live, we'll be off the air in 10 minutes, so I don't care anyway. All right, from there, let's go to, we got a Rosanna talk.
Yeah.
And then we'll do our photos at the very end. So.
Okay.
Okay. So.
All right, let's do the Rosanna talk. Oh! Rosanna's fun fact. The only thing I forgot to do is show you who Rosanna is. I do that every time.
There she is. Just a sec, I'll go to a spotlight screen there again and get that brought in, and I'm going to turn off my mic so you're pretty good to hear us.
Okay, so here we go for this week's
Rosanna's Fun Fact.
All right. Well, welcome back, Rosanna. How are you? Good to see you. And we have another great Rosanna fun fact all set up for us today. And this one's really kind of cool. So I'm going to go right to a photograph that she sent me at first. Okay. So how she starts the fun fact is simple as this. It's called fishing in the dark. So when some things have been on hold throughout the pandemic, the quest for answers about what's in the dark has not been ebbed. Fishing around at the center of the galaxy has led to a surprising possibility. What if the center of our galaxy isn't a supermassive black hole after all? What if it is actually a massive amount of dark matter? That flips our currently held beliefs upside down and makes one wonder if someone isn't telling a big fish story. A new study by scientists from Italy, Argentina, and Colombia say that the evidence is stacking up to support dark matter. First, let's look at how and why we think there is a massive black hole in the center of our galaxy, which we call Sagittarius A. Scientists study the orbits of stars around a massive dark area, and from the information they can determine what stars are orbiting. The behaviors of these stars can tell us about what we cannot actually see. So in 2014, scientists observed object G2 pass its closest point to Sagittarius A and become stretched out and distorted, a phenomenon known as drag. This scientist from the International Center for Relativistic Astrophysics in Italy says it's a sign that Sagittarius A might be something other than a supermassive black hole. Now, in 2020, the same research team publishing findings, and then there's a link. I'm not going to put it up now because it's just a page and about the findings, that G2 and S2 might be experiencing the same different kind of gravitational pull near Sagittarius A. They say that way these objects behave is the way that these objects behave is more consistent with a specific kind of dark matter. In their side-by-side analysis of black hole versus dark matter as the explanation, dark matter was a better statistical fit. So in another new study, which again I won't show you right now, this was accepted for publication by MNRAS Letters. The Italian, Argentinian, and Colombian scientists explain that not just the directly affected G2 and S2 space objects line up with the dark matter theory. They've explained that their study to the closest, most well-understood stars orbiting Sagittarius A and found that those stars also behave consistently with the dark matter model. So why does it matter about dark matter? What is dark matter? And well, I can't show you that, but I can show you this. No, that's not. Roseanne is definitely not dark matter. There we go. Dark matter is stuff we can't see, but we can measure it by its effect of gravity and objects around it. Think wind. So you can see the flag or leaves move in the wind, but you're not actually seeing the wind. So scientists estimate that the dark matter makes up 27% to 30% of the mass of our universe. And along with its cousin dark energy, together they make up a total of 95% of the mass of the universe. So more importantly, dark matter can and does turn into black holes. These new studies suggest that Sagittarius A will require a lot more material, hard to imagine, in order to turn into a black hole. So for now, the term is a dense blob. That's not nice, eh? That is still attracting nearby objects, like this gorgeous super jock stereotype at a party. That's who he is. That's the picture. If it is kind of prototype future black hole, that could explain how supermassive black holes form in the first place, something scientists have been puzzled by for decades. So if you find this unsettling, you can sympathize with how marine biologists might feel right now. Oh, where's my little arrow? A little fishy in the water. How marine biologists might feel right now. An international team of marine biologists has recently found that mesopelagic fish in the Earth's oceans can constitute 10 to 30 times more biomass than previously thought. UWA Professor Carlos Duarte says mesopelagic fish that live between 100 and 1,000 meters below the surface, must therefore constitute 95% of the world's fish biomass. So whether you're fishing in the dark of the universe or the deep dark of the ocean depths, you're bound to catch some exciting new knowledge. Now, we're going to find the gag. Oh, there we go. And that was this week's
Rosanna's Fun Fact.
Yay!
fantastic.
That's awesome.
So interesting. She always comes up with the coolest
Oh,
stuff.
she does. Yeah.
That's awesome. Yeah.
Yes, indeed. Thank you, Rosanna.
Thank you very much. So yes, awesome. Okay, let's get to our last little sections here. We're gonna get to a few photos that we've got, and then we're gonna play just a quick little video because I know we're running long tonight. Didn't mean to, but I guess we are. Yeah. Long. Okay, you know something? I might have been able to present my other screen earlier, but I don't know. Let me go that way. I'll check it out later. Okay. Anyway. Got some different photos here to show before we get started with the ones that I had asked people to graciously send in to me. So I have a few here to show. Oh, it's not presenting on the wrong screen again. Here, I could drag this one over. This is easier. Okay. There, can you see that one?
Yep, looks good.
So this one comes from Stefan Picard. Stefan says, hi Chris, still going through captures from the last month or so since we've been only getting clouds now for over a week. Yes. Agreed. Here's the Milky Way from May the 15th and keep noticing the rich amounts of targets within this part of the sky. So yeah, there's a pile of stuff in this area for sure.
Very nice.
Yeah, it's beautiful.
Awesome. Thank you, Stefan. Lisa Ann Fanning sends in, hi Chris, sunspots for today, June 30th, she said, taken with a white light filter over Swarovski spotting scope. Easy to say, yeah. Swarovski, thank you. And Celestron XYZ adapter. I'm still learning the new hydrogen alpha scope I recently purchased. Awesome. And she says she has a coronal photo here too.
Oh, nice.
Beautiful. Good shot. Nicely done, Lisa.
Yeah.
Jamie Wanat says this one in. Hi, Chris. I took these early Wednesday morning. The little orange dot on the left is the moon between the trees, and the bright one is obviously Jupiter. The second one is the moon rising up over the trees, Jupiter and Saturn. That's her second photo. And this is her first photo right there.
Oh, nice.
Unit scope sitting there.
There we go.
Looks like you got some nice dark skies here, Jamie.
And no trees.
And no trees, yeah. No
And
trees to cut
some
down.
Starlings by your house.
Yeah.
Yeah.
Okay, so that's about it for the photos I think I had. And I'm going to go from there to what else I had to show. Just a second here. Get that opened up, and I think it's in here somewhere. Where'd I put it? Oh, hang on a second. It's rearranged it on my desktop, of course. I'm just going to pause here for a second. I'm going to stop presenting for a second until I find it. Here it is. Okay. I found it. Okay. One more time. These live shows, eh? Okay. Let's see if I can get this one up and running. And should be in the right spot. There we go.
Wow. Any single one of those, and every single one of those could be a postcard shot. Honestly, they're gorgeous.
Yeah. Amazing.
Wow. Those are incredible.
Oh, nice. Yeah. Yep.
But the audience can't hear me. There, sorry. A live show. Here we go. That's all because of this new guy here that I might have to sell. Put this up on eBay tonight if anybody wants to buy it. Anyway, I want to say thank you for everybody for offering those photos. It was incredible. Karim, again, I mentioned that I'd like to get your photo up here on one of my Facebook pages, posts later on, about that pinhole camera, one that you've done with the sun. You can actually see the sun moving up through the sky throughout the season. I think we're all good now, okay? So, yeah, okay, great. Well, that was fun.
Yeah.
More experimenting than anything, but this is how we learn this kind of stuff. I'll go back and watch this replay later to see where I screwed up as much as I did. It's always come back to me. Yeah, that's what it's like being a host.
Just to answer that question with somebody about that bridge camera, so long as the camera itself, you can put it into manual. If you can run the camera totally manual, and then run it with either remote or your phone or something, a lot of the things we're going to talk about, you can use that type of camera.
Okay.
Yep.
Awesome. Thank you, Paul. So I want to thank everybody for joining us here tonight. So before closing tonight, we want to remind you about our show next week. Next week's show, we realize the little ones are out of school now, and they're looking for things to do. So we thought we'd try to offer some fun projects that kids can try at home with the family or friends, and maybe a few websites that they might want to visit as well, with some interesting stuff. So so our show next week will be dedicated to the interest of kids. So in closing then tonight, again, thanks very much for your wonderful continued support out there. Again, thanks to Rosanna for her contributions to the show. Really appreciate them. We really do appreciate all your efforts in helping us put the show on, and we also would like to thank all of you out there who share our program with others. Thank you very much. And remember too, we do love getting your photos, so send them into SundayNightAstronomyShow@gmail.com. I'm going to keep using that address for right now. And we're happy to put them up on our next broadcast. Also looking for suggestions for future topics for other shows. Actually, tonight's topic came from somebody out there, one of the followers, who asked us to talk a bit more about the sun. They said the solar eclipse had passed, so they were hoping for us to talk about the sun, and we hope we covered that topic for you tonight. So if you have anything that you'd like us to add on a future episode, please send your request to the same address, SundayNightAstronomyShow@gmail.com, or just send them into my Facebook page, and we'll be happy to make them happen for you. Also ask that if you enjoyed the content here tonight and you joined us from YouTube, please consider giving us a like and subscribing to our channel. And please let your family and friends know that we are here every week, every Sunday night, at the same time to help educate you on the night sky. Entertain you too, like with the live feeds, it's always something going on. Anyway, we're here, we made it through the show, that's another week we can put behind us. So for now then, from Mike, Paul and I, stay safe everybody out there. We wish you all clear skies. We're hoping to get some skies here clear for ourselves very soon. And we hope to see you again here next week. And as we like to say, guys, keep your scopes pointed up.
Point it up.
Thanks, everybody. Have a great week. Good night. Cue the music.
These are not the show problems you were thinking of having.
Definitely not. everybody. Have a great week. Good night.